because see, observe, all the parameters in this are mechanical parameters. Slip and speed, both are mechanical parameters. Okay. So this will give the relationship of torque and slip. So here you can observe from equation, what we can say, yeah, 7, rotor copper loss to rotor input is just a slip. Okay. And from this equation 7, 8 and 9 and 10, okay, we can see all the performance parameters like rotor copper loss. So what is rotor copper loss here? Rotor copper loss is equals to slip into rotor input. Okay, so what is rotor input? P2. Okay, rotor input P2 is also in terms of slip. Okay. So like this, okay, here it is rotor input P2. So once I know the slip and rotor input, I can find out all other parameters here. Okay, so these are the relationships which are important for us. So without knowing resistance, without knowing reactance, without knowing what we say, the load condition, we can find out the performance of the induction motor on, based on the slip value. So many times I told in the previous classes that slip is very, very important for us in an induction motor. Okay, so many of the things, many of the performance parameters are calculated based on the slip value. Okay, so next we will move to induction motor torque equation. We will relook into the torque equation from other perspective. Okay, induction motor torque equation. So the gross torque TG. Okay, so this is the torque developed in the rotor. Gross torque TG developed in rotor, okay, is TG is equals to, I can write P2 divided by 2 pi ns by 60. P2 divided by 2 pi ns by 60. Okay. P2 divided by 2 pi ns by 60. Okay. Also rotor input P2 is equals to, it is slip times rotor copper loss. Here we have seen that rotor input P2, okay, rotor copper loss, sorry, not slip, copper loss is divided by slip. Okay. Rotor input P2 is equals to, I can write copper losses, rotor copper loss divided by slip. So rotor copper loss divided by slip. What is rotor copper loss? So this rotor copper loss is the total rotor copper loss. Rotor copper loss is equals to 3 into I2 square R2. Therefore, P2 is equals to 3 I2 square R2 divided by S. Okay, or I can say IR square R2. It will be more better because so far we have seen the rotor current as IR square R2. Now what is IR? We have IR is equals to, okay, S into E2, okay, divided by under root, that is ER divided by ZR, or I will write this is once again. So IR is equals to ER divided by ZR. So this I will write ER is S into E2 under root R2 square plus S into X2 whole square. S into X2 square. Okay. Therefore, P2 is equals to, okay, therefore P2 is equals to, I can write here 3 into IR square. 3 into IR square. So IR is S square, E2 square divided by square root will go off into R2 into 1 by S into 1 by S. So this S, 1 S will go off. Okay. So I can write P2 is equals to, I can write P2 is equals to 3S E2 square R2 divided by R2 square plus S X2 square. Okay. You take for time being, what you do is you take this as equation 1. Okay. This as equation 2. Okay. Now if I substitute equation 2 in equation 1. Okay. Substitute equation 2 in equation 1. So we get Tg is equals to, okay, P2 is what? 3 S E2 square R2 divided by 2 pi ns by 60 into R2 square plus S X2 square. Or I can write this as Tg is equals to 3 divided by 2 pi ns S E2 square R2 divided by R2 square plus S X2 square, where ns is ns by 60, synchronous speed in RPS. So what is this 3 divided by 2 pi ns? Is it K1?
Yes, sir.
Okay. Or I can write running torque TR is equals to K1 S E2 square R2 divided by R2 square plus S X2 square, where K is equals to 3 divided by 2 pi ns. And this equation we have used many a times. So this is where from K1 has come. K1 or K. Some books they have taken K1, some books they have taken K. So we have taken K1 for rotor torque. See, this rotor torque is nothing but the torque developed by the rotor, which is gross torque. So this equation always give us the gross torque. This equation always give us the gross torque. Okay. So we'll solve some example. Is it clear, this part? This derivation is only to show from where this k has come or k1 has come. Sorry. Okay. Next, we will solve one or two examples here. A 440 volt three phase, (50 Hz) 4-pole star connected induction motor has a full load speed of 1440 rpm. The rotor has impedance of the rotor has impedance of 0.5 plus J 4.5 ohms per phase. Ohms per phase. The transformation ratio is 0.82. Calculate first point, full load torque, second, rotor current and full load rotor copper loss, third, power output, if rotational loss are (500 watts), maximum torque and speed, and its or maximum torque and speed at maximum torque. Next, starting current. Starting current means always it is a stator current. The starting torque. So these are the given things and are to be solved. So solution. So given things are what? V is equals to 440 volts. Okay. F is equals to 50 Hertz. P is equals to 4. It is star connected stator. Okay. Full load speed N is equals to 1440 rpm. Okay. Then rotor impedance R2 is equals to 0.5 ohms and X2 is equals to 4.5 ohms. Transformation ratio. Here observe what I told in the previous examples. If the transformation ratio mentioned is greater than 1, then it is stator to rotor. If the transformation ratio mentioned is less than 1, it is rotor to stator. This you have to keep it in mind, or else you will end up doing the wrong calculations. Okay. So here K is equals to our transformation ratio. We will write in detail. Transformation ratio is equals to rotor EMF to stator EMF or rotor turns to stator turns is equals to K is equals to 0.82. This you have to please keep it in mind. Okay, if the transformation ratio mentioned is greater than 1, it is from stator to rotor. If the transformation ratio is mentioned from is less than 1, it is from rotor to stator. Nowhere in the textbook this point is mentioned. This is through understanding. Because in an induction motor, the rotor turns are always lesser than stator turns. The rotor induced EMF is always lesser than stator induced EMF. Okay, so this is by default. Therefore, my transformation ratio rotor to stator is always less than 1, stator to rotor is always greater than 1. So always induction motor is a step down transformer. Always induction motor is a step down transformer whose K is less than 1. You should please keep this in mind. Next. Yeah. So other things you have to calculate. I will not rewrite that. We'll move. So first thing what we need to know is the slip. Okay. So slip S is equals to Ns minus N divided by Ns. So Ns is equals to 120 F upon P, that is 120 into 50 divided by 4 is 1500 RPM. Therefore, slip S is equals to 1500 SCF we can take, full load slip, minus 1440 divided by 1500 is equals to how much we get? It is 4%, 0.04. Okay, then to find the full load torque, see, first thing what I need to is full load torque. So TF is what? It is K1 S into E2 square. So I need to know E2. Okay. So E1 is equals to V by root 3 per phase. E1 is always per phase EMF. Okay, so it is 440 divided by root 3. How much will get? Am I audible?
Yes, sir.
Yeah, connection is fine. No? It is 254 volts. Therefore, E2 is K into E1. That is 0.82 into 254. So it is 208.3. 0.3 volts. Okay. Therefore, what is the first point to be calculated is full load torque. Full load torque TF is equals to K1 S E2 square R2 divided by R2 square plus S X2 its square. Okay. This I will write this as it is 3 divided by 2 pi ns Here I can take ns is equals to ns by 60, which is equals to 25 rps. Okay, 1500 revolutions per minute, 25 revolutions per second. Okay, into s e2 square r2 divided by r2 square plus s into x2 its square. So I can write TF is equals to, and this TF is nothing but my TG. Okay, you should not forget this. TF is nothing but my TG. This is the torque developed in the rotor. This is not the torque transferred to this load. Torque transferred to the load is TSH. This is full load torque developed. You can observe here. Full load torque developed. Always the equation, whatever we have seen, this equation is the torque developed in the rotor. So the developed torque is always the gross torque. Okay. Now 3 divided by 2 pi into 25 into s 0.04 into e2 square, 208.3 square into r2 0.5. R2 is 0.5, right? Yeah. Divided by R2 square. 0.5 square plus 0.04 into 4.5, it's a square. X2 is 4.5, right? 4. Now this is equals to TG and TF or TG. So how much we get here? 3 into 0.04 into 208.3 square into 0.5 divided by 25 into 25 into 0.5. This 58.68 Newton meter. .68 Newton meter. Is it right? All are getting the same?
Yes, sir.
Yes?
Yes, sir.
Then the second point to be calculated is rotor current and rotor copper loss. Rotor current, IR, and rotor copper loss. Okay. So IR is equals to, it is, we have ER by ZR, which is S into E2 divided by under root R2 square plus S X2 its square. Okay. So 0.04 into 208.3 divided by under root 0.5 square plus 0.04 into 4.5 square. It is 15.67 amperes. Is it same?
Yes, sir.
Okay. So full load copper losses is equals to, so this IR is nothing but my current per phase, and R2 is nothing but my resistance per phase. So full load copper losses is equals to 3 into IR square R2. Okay. So whatever the calculations we are finding here, these are per phase values. So 3 into IR square into R2. So 3 into 15.67 square into 0.5.
368.32.
Yes,
368.32.
368.32 watts. Okay. These are the total copper losses in the rotor copper losses. Okay. Next, what is the third point to be calculated? It is power output if rotational losses are 500 watts. Okay. P out if rotational loss equals to 500 watts. If rotational loss equals to 500 watts. Okay. Now, what is P out? I can write power developed in rotor PM is equals to rotational losses plus output power. This you can observe from power flow diagram. Okay. So here, this is the power developed in the rotor. If I deduct the rotational losses, then I get power output. So power developed in the rotor PM is the sum of rotational losses and the output power. Okay. So now I know the rotational losses. I can calculate power developed. Okay. So therefore, here P out is equals to PM minus rotational loss. Minus rotational loss, and PM is equals to what I can write? 2 pi. Okay. NTG by 60. Okay, or 2 pi N TF by 60. Both are same, TG or TF. Okay, equals to 2 pi into N. What is the motor speed at full load? 1440 by 60 into TF. It is 58.68 RPM, Newton meter. Equals to. Okay, this is power developed. So when the power is developed in the rotor is rotating at certain speed, and that speed is N. Here you should not take synchronous speed. That is power input to rotor. This is power developed by the rotor. So power developed by the rotor is equals to power input minus rotor copper losses. Okay, so this is equals to
8844.25.
88
44.25.
8848.
8844.25.
Oh, sir, 8848.73.
Yeah, 8848.73.
3.
Yeah, you please check. You might have missed some this one. I think instead of taking pi, you might have taken 3.14. Therefore, that is the difference you will get. Is it? You might have taken 2 into 3.14 into 1440 into this value. Therefore, you are getting less. You directly substitute pi. It will be more correct. Okay. Yeah. Now I have PM. I know rotational loss. I can find out P out. So P out is equals to 8848.73 minus 500. So this will be P out is equals to, okay, 8348.73 watts. Okay. Then next part is maximum torque and the speed at which maximum torque occurs. Okay. So maximum torque and speed at maximum torque. So how you can get maximum torque? T max is equals to, I can write K1 your direct expression plus is after 12 o'clock. Okay. So the expression for maximum torque we have K1. I forgot that. E2 square by 2x2. Is it? K1 E2 square by 2x2. So all the values we know. So it is 3 divided by 2 pi into 25 into 208.3 square by 2 into 4.5. Square divided by 2.25 into 2 into 4.5. It is 92.07 Newton meter. Is it?
Yes,
Yes.
92.07 Newton meter. And the speed at which it occurs. So once I know the slip at maximum torque, I can get the speed at maximum torque. Okay. So slip at maximum torque. Yes, B is equals to R2 by X2. Okay, so this is 0.5 divided by 4.5. Is 0.11. Therefore, speed N is equals to Ns into 1 minus SB. Or N max I can write the speed at maximum torque, not maximum speed. Okay. So Ns is 1500, 1 minus 0.111. So N T max, I will write N T max rather than N max. So it is 1333.5 RPM. 1333.5 RPM. What is next point to be calculated? It is starting current. Okay. So starting current So starting current is to be calculated at primary side. Okay, starting current is to be calculated at primary side. So I can find out the standstill current I2, okay, and transfer it to primary. One case. Second case, I can transfer the impedance to primary, then calculate the current at primary. Okay, rather than doing the transfer of impedance, okay, I will first calculate the standstill current. Okay. Rotor current at start is I2, which is equals to E2 by Z2. The second one. Okay. So it is 208.3 divided by Z2 is under root 0.5 square plus 4.5 square. Okay. So this 46 amperes. Therefore, stator starting current stator starting current IST, okay, is IST is equals to K into I2, that is 0.82 into 46. I will tell you why 0.82. It is 37.72 amperes. Because transformation ratio is E2 by E1 equals to T2 by T1 equals to I1 by I2. So I1 is the stator current here. Therefore, stator current is equals to transformation ratio multiplied by rotor current. Why multiplied by rotor current? Because transformation ratio is less than 1. This always you should keep it in mind. Okay. If it was greater than 1, then it would have been 1 by K into I2. Okay. Starting torque. Okay. Last point to be calculated is starting torque. TST is equals to K1 E2 square R2 divided by R2 square plus X2 square. So this is 3 divided by 2 pi into 25 into 208.3 square into 0.45 divided by 0.5 square plus 4.5 square. Yes?
So R2 is 0.5.
Oh, sorry. 0.5 square. Did I take the same here? Sorry. 0.5 square. Yeah, TST.
Ten point 10.
It is 0.5, not square. R2 is not R2 square.
So 20.
20.21.
Yes, sir. Yes, sir. अम्मी बातें मत करो.
So this is the solution for the given statement. Okay, we'll solve one more or two examples in the next class, and then we'll move to the phasor diagram and synchronous watts. So tomorrow afternoon I may be taking the class. Okay, so today afternoon actually I had planned, but just now I got one additional work to be accomplished. So I may take tomorrow afternoon an extra class. Okay. I thought of taking today and leaving tomorrow, but some crucial work has come to be accomplished immediately. So I have to do that.